Question 45 is a straightforward air heating problem for mixed air. The difficulty is in unpacking the nested variables and prioritizing your path to the solution. Initial critical thought solution elements. 1. What are you solving for? The steady state hot water flow required to heat mixed air to a desired temperature. 2. What is the fundamental process? Energy flow for water and moist air mixing. 3. What are the first considerations to find the solution in connection to the fundamental process? Connecting the properties of standard moist air to a coil's heat transfer rate. 4. Are there key assumptions? Adiabatic mixing, sea level conditions, standard air, and steady flow. This video is brought to you by ExOverZero, which offers the best PE study tools possible. To purchase our practice exams, use the link below. Because the problem is so clearly an air heating process, the first element to identify is BTU per hour. After all, energy flow in the form of BTU per hour is central to heat gain calculations. But it's not given in the problem. So identify what's needed for steady-state energy flow using water as the fluid. Here is the standard heat transfer rate equation used for water. You should have this memorized. You'll need to use it frequently in the exam. Energy flow in BTU per hour is equal to volumetric fluid flow in GPM times 500 times delta T. The 500 in this equation comes from standard condition values of water-specific heat at 1 BTU per pounds degrees Fahrenheit times water volume conversion at 8.34 pounds per gallon times time conversion of 60 minutes per hour. Notice these units and values are obvious if you start with GPM and degrees Fahrenheit and need to arrive at BTU per hour. This is standard unit analysis and critical thinking. You'll ultimately need to solve for fluid flow GPM. You're given a delta T of 40 degrees Fahrenheit. Now, this represents the heat transfer rate from the water. To find this energy flow, look to the heat transferred to the air that's being heated by the coil. All air temperature values are given in dry bulb. So use the sensible heat equation, which is only a slightly different version of the water heat transfer rate equation just used. You should have this memorized too. Energy flow in BTU per hour is equal to volumetric fluid flow in CFM times 1.1 times delta T. The 1.1 in this equation comes from standard condition values of air-specific heat at 0.24 BTU per pounds degrees Fahrenheit times air volume conversion of 0.075 pounds per cubic foot times time conversion of 60 minutes per hour. Again, standard unit analysis and critical thinking to move from CFM and degrees Fahrenheit to the solution of BTU per hour. Notice the similarities between the two. You're given the flow of 10,000 CFM. You're given the ending temperature of 160 degrees Fahrenheit. You'll need to find the beginning temperature to solve for energy flow. The entering air temperature is mixed air, so you'll need to do a mixed air temperature calculation to find the entering air conditions. The NCEES solution uses CFM to determine the mixed air temperatures. Note: this is a quick and dirty approximation technique. It can't be used on all mixed air circumstances and be sufficiently accurate. ASHRAE Fundamentals Chapter 1, Equation 44, instructs you to use mass for these calculations. Using mass will always get you the accurate answer. Don't use CFM. Sometimes it's wrong. See question 57 in the NCEES practice test for an example of the trap set for those who use CFM. Look up the dry air specific volume of the two entering airstreams in the NCEES Mechanical Reference Handbook in section 7.4. At 30 degrees, the specific volume of dry air is 12.338. At 70 degrees, the specific volume of dry air is 13.349. Take the reciprocals and multiply them by the volumetric flow to get mass flow. The total mixed airstream flows at 10,000 CFM. The 30-degree airstream flows at 2,000 CFM. So, the 70-degree airstream is derived as the remaining 8,000 CFM. 2,000 CFM times 0.081 equals 162.1. 8,000 CFM times 0.075 is equal to 599.3. Total mass flow of the combined airstreams is the sum of these two, 761.4. The mixed air temperature will always lie on a straight line between the two input airstreams. It's determined by the proportion of masses. Ultimately, you'll only need one, but both are done for illustration purposes. The 30-degree airstream is 0.213 of the total mass. The 70-degree airstream is 0.787 of the total mass. These ratios are applied to this line, but be sure to put them in the correct position. They do not go like this. Take a moment to internalize this as critical thought. They may seem backward. Think of it like the weight of the mass of the 70-degree airstream is pulling down. It's a bigger mass, so the temperature which needs to lie between the two airstreams should be closer to 70 degrees than to 30 degrees. The difference between 70 degrees and 30 degrees determines the length of this line, 40. 78.7% of 40 is 31.48. So the mixed air is 31.48 degrees above 30 degrees, making it 61.48 degrees. Now you have everything needed for the sensible heat equation. Energy flow in BTU per hour is equal to 10,000 CFM times 1.1 times 160 minus 61.48. This is 1,083,720 BTU per hour, which represents the amount of heat transferred into the air. Therefore, it's the amount of heat transferred out of the hot water coil. Going back to the original heat transfer equation for water, 1,083,720 BTU per hour is equal to the volumetric fluid flow in GPM times 500 times 40 degrees. This equals 54.19 GPM. The correct answer is A. Remember, the slight difference in calculated numbers comes from using the more accurate mass values to determine the mixed air temperature. The NCEES solution is a dangerous approximation, using CFM to determine the mixed air temperatures. Even with the different calculation technique, the method provided here gets the correct answer. To get good at questions like this, go through Example 4 in ASHRAE Fundamentals Chapter 1. Also do ExOverZero problems number 45 and number 57 in tests 1 through 4.